The half-life of professional skills is shrinking. As technological cycles compress, traditional multi-year education can no longer keep pace with the modern economy. In 2012, Scott Young tested this constraint by attempting to learn MIT's entire 4-year undergraduate computer science curriculum without taking any classes. He passed the final exams for 33 classes and completed the required programming projects in 12 months. Professional resilience rests on learning agility, the capacity to systematically and rapidly integrate new, complex models on demand. High-speed acquisition depends on architectural efficiency. Success stems from the structural design of the learning project rather than raw innate intelligence. This algorithmic diagram maps a 6-phase workflow designed to structure that efficiency. It merges cognitive psychology with neurobiological optimization to streamline the learning process. Mastering this specific meta-skill allows you to weaponize your cognition, providing a mechanism to remain relevant as automation and technological shifts restructure the workforce. Phase 1 requires meta-learning, learning how to learn a subject based on its inherent structure. This mandates the 10% rule. The first 10% of total project time must be spent researching the domain before committing any resources to actual study. This matrix shows the CFP model, deconstructing information into 3 buckets: concepts, facts, and procedures. Under concepts, we target core ideas for deep understanding. These are processed using the Feynman Technique, a logic tree method of simplifying ideas to expose gaps in comprehension. Physicist Richard Feynman used this method of first principles breakdown to cultivate his intuitive expertise. He avoided memorizing equations, choosing instead to imaginatively reconstruct concepts from the ground up until they reached a visceral simplicity. The facts bucket contains isolated units of information. These are encoded using spaced repetition systems, which carefully schedule reviews precisely as the brain is about to forget them. Finally, procedures are sequences of actions practiced deliberately and drilled until they reach automaticity. Failing to categorize knowledge into this matrix prior to execution results in wasted cognitive bandwidth. Without a map, the learner applies suboptimal acquisition strategies to the wrong type of information. In Phase 2, we apply the DIS-S framework: deconstruct, select, sequence, and stakes. We prioritize selection using the Pareto principle. This curve demonstrates learning's asymmetry. 20% of the material generates 80% of the utility. In language, targeting the 1,200 highest frequency words crosses that 80% utility threshold. Pursuing the remaining volume requires an exponentially greater time investment for diminishing returns. To find those high-yield units, we deconstruct the complex skill into its absolute smallest possible parts. Then we select. This involves ruthlessly filtering out the low-value material that leads to diminishing returns, ensuring effort is spent only on high-impact components. Once the high-value components are isolated, we enter Phase 3, strategic sequencing. This phase relies on the inversion method, putting your learning in an order optimized for momentum rather than traditional academic progression. Traditional starting points often lead to early frustration by front-loading complex theory. Instead, start with simple, high-impact endgames to establish intuitive mental models and early confidence. Applying strict Pareto selection and inverted sequencing helps maintain momentum, preventing a learner from abandoning a project during the earliest stages of friction. Phase 4 is intensive acquisition. This requires a strict commitment to a minimum of 20 hours of focused, concentrated practice to bridge the gap between incompetence and initial automaticity. Those first 20 hours represent the frustration barrier, a period of severe cognitive resistance. It is breached through sheer volume of practice. During this push, you must apply the principle of directness. The skill is practiced in the exact context where it will be applied, avoiding the loss of information when classroom knowledge fails to transfer to the real world. Direct practice reveals weaknesses, which are addressed through the drill. You isolate the rate-determining step, the absolute weakest subskill, and attack it ruthlessly. Combining direct practice with targeted drills over a focused 20-hour window forces the transition from abstract theory to functional, real-world execution. Phase 5 is retrieval and feedback integration. Passive study, like rereading notes, creates an illusion of competence but fails to encode knowledge. This tracks the Ebbinghaus forgetting curve, showing how quickly passively acquired knowledge decays if left unretrieved. To combat this, we force the brain to retrieve information without reference material. Vertical spikes show active recall sessions resetting the baseline and stabilizing memory retention at higher levels. We combine this with interleaving, the practice of mixing different subjects or problem types to stress test neural pathways and force the brain to identify the correct strategy. Active retrieval must be paired with immediate, accurate, and corrective feedback loops to ensure the information being encoded is correct. Chess grandmaster Judith Polgar mastered her domain through this mechanism, training in highly structured environments filled with immediate feedback and active problem-solving against elite opponents. Processing negative feedback requires isolating the objective signal, the specific area for improvement, from the emotional noise. Without stress testing memory through forced retrieval and feedback, acquired knowledge remains fragile under professional pressure. Phase 6 is neurobiological optimization. While behavioral execution occurs while awake, the actual structural learning happens during sleep. During rest, the hippocampus and cortex engage in systems consolidation. This biological process stitches isolated memories into cohesive, unified cognitive maps. This cross-section shows myelination. As you learn, the brain physically thickens the myelin sheath, a protective coating around the active neural pathways. This physical thickening is directly driven by the repeated retrieval cycles executed in Phase 5. As the myelin sheath thickens, electrical signals travel noticeably faster and with greater reliability, dictating the speed and efficiency of the newly acquired skill. Hardening these cognitive maps creates a strict biological requirement: 7 to 9 hours of quality sleep. Without adequate systems consolidation and myelination during sleep, the rigorous behavioral protocols executed during the day will rapidly degrade. By aligning architectural learning strategies with these neurobiological laws, professionals can weaponize their cognition to master any complex domain on demand.